Okay, welcome everyone. Today our speaker will be Majid Khadiv from the Max Planck Institute in Tübingen. Majid is an expert on optimization and control of legged robots, in particular humanoid robots. Before joining the Max Planck Institute, he did a master's and a PhD at the KN2C University of Technology in Iran, where he worked on algorithms for humanoid walking. And since 2018, he is a postdoc at the Max Planck Institute, where he currently works with Ludovic Righetti on the control of legged robots. So I would like to thank you, Majid, for joining us today, and I'm really looking forward to your talk.
Okay, thanks a lot, Andreas. Let me see if I can share my screen. Okay, can you see my screen?
Yes, perfect.
Okay, great. Thank you so much for having me today here. So today I'm gonna be talking about control of legged robots in especially in challenging environments. But the first question is, why legged robots? If we look around ourselves, we can see that there are a certain number of jobs out there that are very dangerous for human beings, but at the same time, they need a certain amount of dexterity like human being. The research we do in legged locomotion and the knowledge we gain can be used to design and build exoskeleton and prosthetics. Also, humanoid robots can help us, can help elderly people. They can be used to teach our children, to entertain them. They can be used in home care services and so on and so forth. So with this picture, we can see that there is a huge amount of applications out there for these robots, given that, provided that these robots are able to show some performance close or incomparable with human beings. But the problem is that legged locomotion is extremely hard. Why it's hard? Because first of all, these robots have unilateral contacts with the environment with different parts of the body. They are unstable, inherently unstable, which means that they can easily fall down if they are not controlled properly. They have some state-dependent switches, and they need these switches in order to move their body in a certain directions. They can be prone to external disturbances, environmental uncertainties, perception uncertainties. Also, the contact forces can be even more limited in certain situations. And finally, these robots have many sensors and actuators, and these sensors and actuators should be working simultaneously, synchronously, such that the robot is able to achieve a desired task. So in this picture, you might see that it's really hard to control humanoid robots in general. The way I tackle this problem is by using a combination of model-based control and machine learning to control legged robots. Okay, let's take a look at the structure of the dynamics. So these robots have a continuous part of the dynamics, which is an ODE, and we have the actuation have some limits. So we have a constraint on the actuation, and this is valid as long as the robot is not on the switching surface. But as soon as there is a switch in the contact location, there is a switch in the dynamics, and the robot might go to a jump in the states, which is due to impact. So this system is in general a hybrid system. If we take a closer look at the continuous part of the dynamics, we can see that we have an actuated part and unactuated part that we can separate. The actuated part is simple. It's like a manipulator dynamic. So we have torque at the joint. We can use this torque to exert force to the environment. So this part is fine. The unactuated part is the main problem, is that we need to exert some limited amount of force to the environment to control the center of mass motion. And these dynamics can be captured using centroidal momentum dynamics, which says in order to control the center of mass, we need to control the sum of contact forces on the environment. So this is a nonlinear non-convex dynamics in general. However, there are some certain linearization or simplified version of this dynamics. For instance, if we say that the height of center of mass is fixed and there is a negligible rate of angular momentum around center of mass, we can use a linearized version of this dynamics to plan motion for this robot. And this is the normal control pipeline we use. to control these robots. So we are given a desired behavior. We generate trajectories for the most important parts of the robot, which are the end effectors and the center of mass. Then we have a whole body controller that stabilizes the system around this trajectory using feedback. So the trajectory optimization part can be done either offline, but if we can do it, if we can regenerate motions very fast, we can use it inside an MPC loop. So the first question I would like to tackle in this talk and talk about in this talk is how to control walking. So we have different types or different designs of humanoid robots in terms of leg design. So on the right, for instance, you can see Hermes, which is a fully actuated robot with ankle joint, with toe joints. All of them are actuated, and the system is kind of heavy, but it has full control authority and the contact forces. So the problem with this robot is that the leg is heavy, so we cannot achieve very dynamic motions. On the left, however, you can see a minimal design of the leg. So the robot doesn't have any ankle joint, it doesn't have any ankle actuation, the legs are light, so it should be able to do very fast motions. But at the same time, the control of contact forces becomes very challenging. The robot might rotate around the normal axis to the environment because there is not enough rotational friction available for this robot. So a trade-off design would be the robot in the center, which has unactuated ankle, but it has a foot, and this foot can generate the rotational friction, but we don't have full control authority at the contact. The question I would like to answer is that, is there a single walking controller that enables all these robots to walk robustly? My answer or my approach to this problem is model-based control. So if we go back to the equations here, because we want to tackle only walking, we would resort to using simplified dynamics, which is LIPM, which is a very good model very good model for walking motion. And here the idea is that rather than controlling the continuous part, we only rely on the switching part of the dynamics to control walking. So the idea is that if we only control the location and time of the next contact switch, we should be able to control walking and stabilize the unstable dynamics of the center of mass. So this is the main idea here, because we don't have full, because we want to control all these robots, and some of them don't have enough control authority to control, for instance, center of pressure. So what we need to do here, what we propose to do, is that to only adapt next step location time as a function of feedback to control these robots. Okay, this is the program we solved. We find the next step location UT, the step timing tau, which is exponential step time here. And we defined a parameter B of t, which is the distance between the unstable state of the center of mass dynamics and next step location. And we use this distance as an index for stability of the system. So what here, in the cost, what we try to do is that we've tried to find UT, next step location, as close as possible to the nominal values, times as close as possible to the nominal values. And then we have the third term, which is the terminal cost on the system, which tries to limit or bound the distance between unstable state of the center of mass dynamics and the next step location. And with this, we are able to provide some guarantees for this system. We have certain constraints. So next step location is limited, timing is limited, we have the dynamics of the system. And finally, the last constraint is the terminal constraint we have on the problem, which says at the time of contact, the DCM offset that we defined between the unstable part of center of mass dynamics and contact location should be limited. And these limits can be found analytically using LIPM. And with this formulation, we can adapt very fast next step location and timing. We can then find the swing foot trajectory to land at a certain time, at a certain position. And finally, we pass all this trajectory to a whole body controller. Here, we use hierarchical inverse dynamics for tracking these trajectories. I implemented this on a robot in simulation. And here the ankle is not actuated. And we were able to generate very robust motion in the presence of different external disturbances, just by adapting next step location timing using the measurement of the center of mass states. So the main thing that we showed in this paper or in this work is that timing adaptation is really important. And it had been ignored normally because it renders the optimization problem non-convex. However, we showed that with this novel formulation of the problem, we can find a convex optimization problem that adapts both step location and timing. And this timing adaptation gives a kind of exponential push recovery capability compared to not adapting it. So the features of the planner, there is no need to explicitly control center of pressure, center of mass. So we don't care so much about the continuous part of the dynamics. We are able to, just by looking at the next switching manifold, which is the next step location and timing, next step location, we can guarantee viability, which is the ability to, the ability to, that it guarantees that there is at least one control sequence or one solution to the problem that doesn't go to the failure. And finally, we can do very fast replanning with step timing adaptation. I started to implement this on the robot, and this is how far I could get. The robot is doing only balancing here with inverse dynamics. We couldn't go further because of many hardware problems we had. I need to be very careful with these robots, which is hydraulic, if you can see in the video. And also we need a couple of people to work with this robot. So it's really hard to manage this robot and do this as a very fast and dynamic experiment on the system. So what I did is that this year with Felix Grimminger, a mechatronic engineer in our lab, we wrote a proposal to build a new biped robot that is easier to handle. It's based on off-the-shelf torque control robot, but off-the-shelf components and 3D printing materials. And the idea was that can we build a robot that is able to do very dynamic motions like this. So we built the robot in February, and then this is the first test we did on the robot in March. And then finally, a couple of weeks ago, with the help of Elham, who is a bachelor intern in our group, we implemented the algorithm with a bit of modification on the real robot. So this is the robot board. It is stepping forward and backwards in this video by only adapting next step location and timing based on the measurement of the center of mass dynamics. So this is, for instance, 10 minutes of test without any pause, and the robot is stepping robustly, and it's tracking the velocity forward and backward. And also sometimes I pull the robot using this wire as a disturbance. The second experiment is uneven terrain. The robot is not aware of all these obstacles and the path. And thanks to the torque control and adapting next step location and timing, the robot is able to deal with this kind of uncertainty. I will move forward a bit. So the third surface is a soft surface. So in the controller, we assumed that the surface is rigid. But here we have a kind of soft surface that causes a bit of oscillation in the robot motion, but the controller was robust enough to deal with this uncertainty. Then we have some push recovery scenarios. We are pushing the robot in different directions, but thanks to the MPC implementation and very fast replanning, we are able to adapt the next step location timing to recover from this disturbance. So here is the push recovery in sagittal or frontal plane. And finally, we have a slippage recovery, which has not been done in the literature on bipedal robots because it's a very challenging task. But our controller is able to do this. So I'm moving the platform randomly, and the robot is able to adapt in next step location timing to recover from this disturbance. Okay, how about if we want to generate more complex motions? If we want to do multi-contact motions with the legged robots, we want to climb a ladder, we want to manipulate an object while walking, or we want to do very dynamic motion with flight phase, like backflip or something like this. And then we cannot anymore use LIPM, but again, I propose that we use the model-based control. And here, rather than LIPM, we use the full centroidal momentum dynamics, which here is, in this case, is non-convex, non-linear. And also we need to control the continuous part of the dynamics, because we need to have more control authority on the motion because these motions are more delicate than walking. Okay, the trajectory optimization part here, we write down the centroidal dynamic motion planner. So here the main thing is that so what we want to do is that we want to generate trajectories for the center of mass, momentum around center of mass, and contact forces. And the main constraints of this problem is centroidal momentum dynamics, which is non-convex, and the rest are some linear constraints that we can enforce. So thanks to the solver that Brian, a PhD student in our lab, developed, we can solve this problem using a sequence of convex approximations that helps us to solve this problem, this non-convex problem, very quickly. And then what we can do is that we can, once we have a trajectory for center of mass and momentum, we can do one full pass of the whole body inverse dynamics or inverse kinematics around this problem. And we enforce there the whole body constraints like joint constraints, torque constraints, etc. And then by iterating between these two centroidal and whole body solvers, we try to come to a consensus in terms of momentum around center of mass. And as soon as they come to a consensus, it means that we have a trajectory that is consistent with the constraints in terms of contact forces and constraints in the whole body, like joint torque constraint, joint positional velocity constraints. So I started to implement this plan, the trajectories from this planner on Solo. Solo is another robot in Felix built for us in our lab. This robot is also torque controlled. It's open source and it's kind of rather inexpensive. So every lab can download the documentation and all the parts and build this robot. So it's back drivable, which means it's torque controlled. We can do torque control on this system. It can do kind of knee inversion, which is useful sometimes in order to step onto obstacle or move in a very cluttered environment. It can do very simple fall recovery thanks to its design. So the only thing it needs to do is that it would flip the legs. And finally, the robot is really impact friendly, which means that we are not afraid of generating very dynamic motions with impact on these robots. And this helps us to validate the capability of our planner on a real robot. So I started to implement the motions for the first time on a real robot. So here is a slow trot. So here we don't do the trajectory optimization in MPC. We only generate the trajectories offline. And then we use the low-level controller, which here is an impedance controller. We try to track the trajectories. So I did the same test, but here we put a seesaw on the path of the robot. And thanks to the feedback control, the robot is able to adapt to this unknown environment. And finally, this is a faster trot motion. And thanks to the full body trajectory optimization algorithm, even without replanning, we are able to execute this motion on a real robot. So here I'm showing another motion, which is a high jump, to show that the planner is able to generate this motion and the robot is powerful enough to jump more than 5 times its standing height. So the robot standing height is 21 centimeter. And we generate trajectories for the full body, and then we track it using an impedance controller. And the robot can jump here more than 100 centimeter. So the main point here is that thanks to the torque control, we can adapt or modulate the impedance or the gains during the motion. And this is the key to have this kind of jumping motion on a real robot. Because in order to push off and generate enough thrust to jump really high, we need really high stiffness during the first part of the motion and rather low damping. But for the next part, which is the landing part, we really need a low stiffness and high damping such that there is no bounce and the landing is soft. So this is the thing that we needed to do to have kind of clean jump on a real system. This is another motion. The robot combines a kind of static and dynamic motion. So first it's statically stable. It put the feet on top of the obstacle, then it jumps on top, and then again another type of static motion. So again, for all these motions, we would generate the motion offline, and then we would execute it using a low-level controller. But all of us know that these motions don't work at the first try. So what I would do is that I would generate some motion, and I would execute on the real system, look at the motion and the data. I would adapt some parameters of the planner or controller such that eventually we achieve a kind of a desired motion. For instance, here is jumping on the obstacle. So the third question I would like to answer here is that could we use the past experimental data, or especially the failures, to come up with a real robust motion such that we achieve a robust motion in the presence of all the disturbances? And here is the place that I combine machine learning with model-based control to tackle this problem. So here is the work we did with the master student, Muhammad, in our group. So what we want to do here, again, the structure is very similar. We have two-level control. High level generates plan, low level control the try to track the trajectories. But here what we propose is that we use Bayesian optimization to find the optimal cost weights of the planner or a slow MPC here, such that we have a robust motion. So normally what we do is that we have a constrained MPC. So here I'm talking again about walking motion. So I'm doing MPC using a LIPM for walking motion. And then we have here we used for the low-level controller an unconstrained ILQG, but we can do whatever else like inverse dynamics or impedance control. It's fine also. So here, writing down the cost of the slow MPC is the main point of the problem. So what we can do is that we can say for walking problem, we have one term that is related to the performance. Here is walking velocity tracking. So we are given a command, we want to track in the desired velocity in a certain direction. Then we have a kind of interaction forces that are limited. So here, for instance, for walking, we have center of pressure or ZMP that should be as close as possible to the center of the foot such that the motion is robust in terms of contact forces. The third cost term we consider is a step margin. So when you adapt the step location, it's really important that it's far away from the boundaries of a reachable area. And finally, since we are doing finite horizon MPC, it's really important that we have a proper terminal cost such that it guarantees the invariance or brings the system to a state that would not diverge because this system is unstable in general. So the main point of so finding the best cost weights of this problem such that it trade off performance with respect to robustness is the main thing we can do here using Bayesian optimization. And then here we have the constraints of the problem, which I'm not going to talk about here. And then we have this. So let's look at the problem graphically, very simply. So if this, we look at the cost term about the ZMP, if we put beta in this equation to 0, what happens is that most probably the optimizer will find the solution that puts ZMP on the boundaries, because it's one of the most constraining constraints of this problem. But as we increase beta, we are putting a second order cost on this term, which pushes away the solutions toward the center. But this comes at the cost of degrading the performance or putting other constraints on the boundary, or even at the cost of instability of the trajectories. So finding the best cost weights is really important in order to have a robust trajectory. So here we propose to use Bayesian optimization and use past experimental data in order to find the optimal cost weights that gives robust trajectories. So Here we only showed the motion in simulation. We added different types of uncertainties, actuator uncertainties, computational delay, external pushes to the system. And the robot is supposed to walk forward with the desired velocity. We started with a very robust motions, but which means that the performance is really bad. The robot is not tracking the velocity. And we are adding disturbances, external disturbances to the system that sometimes may cause a failure to the system. And at each iteration of Bayesian optimization, we are sampling 50 external pushes from a uniform distribution. And what happens is that Bayesian optimization is adapting the weights, cost weights of the slow MPC problem to find a robust motion. And here, after 13 queries, it could find a solution that the robot doesn't fall at all with all the random disturbances, and it's able to track the desired velocity relatively well. So you can see that the disturbance is different each time, and it's randomly selected from a uniform distribution. And this is the resulting motion. The robot is tracking the velocity well while rejecting the disturbance. And at the end of motion, it manages to stop at a certain position that you want. And here is the history of the Bayesian optimization search. So you can see that after 13 iteration, it could find already a good solution. And if we continue, there is not much improvement we can see. Okay, to conclude, I believe that model-based approaches work really well under real systems. I hope I could show it to some extent. But when we want to use model-based approaches, exploiting the underlying structure is crucial and really important in order to solve the problem very fast. And we can combine model-based approaches with learning such that we have a fully automatic pipeline that gives us robust trajectories to be tracked. And finally, I would like to emphasize that models are really important. I would like at the end to thank my collaborators. I wouldn't have been able to do any of these works without their help. And finally, these are my colleagues in Machines in Motion. We have very nice discussions every week, and it has been very helpful for me. I would stop here. I have a couple of more slides, but I would rather spend the rest of the time for discussion. Thank you.
Okay, thank you.